Good morning, everyone. Can you hear me? Good morning.
Hear you. It's all good. Or I can at least.
Okay. Okay. Did we all see the materials for the lab class today? Okay. Someone made requests for me to upload the lecture videos. The reason why I've not done that is because I want to trim off some part of the videos, and I've not been able to find a simple way to do that. Okay. Soon as that is done, I'll be able to upload the lecture recordings. Right? I hope the person that made the request can hear me. I can't remember who exactly, but a number of us requested for that. Okay. Okay, so today we are looking at the second part of our chapter 2, which is acceleration. Last class, we looked at velocity, velocity vector, uniform motion, interpretation of velocity time graph, how to deduce velocity time graph from position time graph, and vice versa. So today we're advancing a little bit further to looking at acceleration and the time constant acceleration. All right. So what do we really define acceleration to be? We define acceleration to be the rate of change of velocity. Okay. We know what velocity is, and we're used to the term velocity and velocity vector. We also know that acceleration in itself is a vector. So we have the vector representation of acceleration as well, just like we have in velocity vectors, okay? So the equation AX equal to change in V for velocity over time, change in time, is the equation for acceleration. Okay. All right. So we also know that when we discuss velocity, we're able to deduce that the slope of the position time graph gives us the velocity. And now in acceleration, the slope of the velocity versus time graph will give us acceleration. So we'll have the formula for acceleration. We have stated it in words that the rate of change of velocity is acceleration. And we have established now that the slope of the velocity versus time graph will give us acceleration. And acceleration is measured in meters per second squared. Okay. So having done this, let's progress to looking at the representation of acceleration, that is signs of acceleration, like we have the signs of velocity using the position using coordinate system, then velocity using velocity vectors, that is the arrows pointing to a direction. The same thing we have in acceleration as well. We have arrows pointing to the direction because they are vectors. They have magnitude and direction, okay? So this is a typical representation of the velocity time graph. And we have established that the slope of the graph here will give us acceleration. So this side of the slide tells us about three information. It gives us the sign, the graph, and also the pointing out the slope, the kind of slope we'll get from the graph, okay? So this is a typical graph of a moving object. We see here that the acceleration with the arrow sign, which is a vector representation, points to the right. It's pointing to the right. Just like we have in velocity, when it's pointing to the right, it's positive, positive. So we'll have the positive slope giving us a positive acceleration, pointing acceleration direction to the right, positive slope giving us the positive acceleration pointing to the right, okay? Well, we can see this vector, velocity vector representation. It does not necessarily mean that the direction of the velocity vector is the direction of acceleration, no. If you look at the velocity vector, how they are changing, this one is going and increasing the speed in this direction to the right. But this is slowing down, decreasing its speed. You see, slowing down, decreasing its speed to the left. So V here is greater than 0 and V here is less than 0, but acceleration here is increasing to the right, which is positive and is positive. All right. So we look at the negative slope. The negative slope will give us the negative acceleration is pointing to the left, and this is pointing to the left. And if we look at the vector, velocity vector representation as well, we see that the acceleration is actually increasing towards this direction. It's increasing towards this direction, and not necessarily the direction of the velocity vector. So they are different. So we see in this case that when the acceleration is pointing to the left, it's negative. It's pointing to the left, it's negative. When it's pointing to the right, is positive, okay? So don't mix it up with the velocity vector or direction of the velocity vector, okay? So you can see this concept in our test, the key concept session of 2.26. Now, all that we have described here, let us present them in words. From this section of the slide is where we are drawing out this interpretation of what we want to discuss next, okay? So we said that acceleration, like the velocity vector, acceleration is also a vector like the velocity. And when we talk about the direction of acceleration, it does not necessarily point in the same direction as the velocity vector, okay? So the acceleration vector points in the same direction as the velocity vector. For an object, it shows it is speeding up. When the two of them are pointing in the same direction, like we have here in the case 1, that object is speeding up. But when it is in opposite direction, it is slowing down. Now, it does not matter if it is a positive or negative acceleration direction. Once you have the vector and the acceleration pointing in the same direction, like we have in this case, and in this case, that object is speeding up. it could be to the positive direction or to the negative direction. But once they are opposite, that object is slowing down. You should note that about acceleration, okay? So that is one point to note. Then another point to note is the signs. Okay, we have established that the movement to the right, positive, movement to the left, negative. How to identify the speeding up and slowing down object is to compare the direction with the velocity vector direction. So the sign of acceleration is based on the direction of acceleration vector, where it points. Is it pointing to the right or to the left? And it's not necessarily based on is the object speeding up or slowing down. So to identify a speeding up object, you make a comparison of the vector direction with the acceleration direction. If they're in the same direction, it is speeding up. If they are opposites, it is slowing down. But the particular sign, if acceleration is positive or negative, is defined by is it pointing to the right or to the left? Okay, so that's the second point to note. Now, the third point to note is an object that is speeding up. That's what we have been emphasizing. If the velocity and the acceleration have the same sign, and they're slowing down if they're in opposite signs, okay? They're pointing to the same direction or they're pointing to the opposite direction. So let's take an example from the term acceleration and using this equation, okay? So our first example says, from rest, a lion sustained an acceleration of 9.5 meters per second for up to 1 second. How much time does it take a lion to go from rest to a typical recreational runner stop? The stop speed of 10 miles per hour. Now, if you look at the question and the information given in this question, is such that, because it is this kind of question that gave us what we'll be discussing later in the slide, the strategy to solving questions. Sometimes when you are given a question, they don't give you the parameters expressly. Some parameters have to be deduced. Some you have to make some preamble conversion that is like unit conversion to get exactly what you want. Now, in this question, they've established that the lion can actually make an acceleration of 9.5 meters per second in 1 second. Now we'll have a recreational runner whose top speed is 10 miles per hour. And the question is now asking, how much time will it take the lion to get to the top speed of this recreational runner? Okay. So the first thing we did was to put this to the unit that we know, the unit that we can actually relate with, which is in meters per second. How do we get the acceleration of this recreational runner before we can make the comparison? Okay. So 1 mile per hour is equal to 0.4 meters per second. So converting 10 miles per hour to meter per second, we took the unit times 10, the basic over this times 10, to give us 4.5 meters per second. So this is the velocity of the recreational runner. So having known the velocity, we can actually get the other parameters, which is what the question is asking. How much time will it take the lion to get to this top speed? Okay. So yes, analyzing the statement from this, we can typically say that yes, the lion can actually get to this top speed in less than a second. Okay. But what figure, what is the exact value. So using this same formula of acceleration, we made change in time, because the question is asking us how much time, the subject of formula. So we have our V, our final speed, to be this, which is total change in speed, over the acceleration to give us 0.47 seconds. So we can see that from this solution, we can actually make this simple statement that it actually takes that lion less than half a second to get to the top speed of this recreational runner. Okay. Can you hear me?
Yep.
Yep.
Okay, good. So progress to analyzing the velocity time graph, just like we have done in the case of position time graph. So this is just a simple replica of that. Okay, so it's nothing different from what we have done before. We have a velocity time graph. The slope of this will give us acceleration. We established that in our first slide. So if we have a velocity time graph, how can we represent this same graph in acceleration time graph? Just the same way we did for the first is what we're going to do here. So because we have seen this kind of case in position time graph, that is why I didn't have to put so many graph with typical digits, okay? So I'm assuming that we're used to this. We'll just run this reminder. It's just going to run like a reminder of what we used to do. So to take this velocity time graph and represent it in acceleration time graph, what we did is to take the slope of the different segment of this graph. Now this graph has 3 segments, 1, 2, and 3. So we take the slope from here to here, then here to here, then this last segment, first segment, second segment, and last segment. Okay. So taking this slope, put any value here, can be 2. Let's say this one is moving 1, 2, 1, 2. So we'll have 2 and 1. When we compute that, the slope will give us the value, and then we stretch within the time covered, the same way we did the velocity time graph. So come to the acceleration, do the stretch to the time, stand in the position value for the slope, take the stretch. This is a positive graph, a positive slope. So that automatically tells you that the value will be at the positive part of X and Y axis. Then this is a negative slope. So that will give us a negative value. And that's why this one is at the negative part. Okay. So we already know that when we have horizontal lines, the slope for horizontal lines are always 0. So we'll have this at the 0 point. We stretch that to 2 steps time, just like we have in the first graph. Stretch here. When we have vertical lines, we have already established that that slope is undefined. Okay, so if this speed is going straight to the point that it becomes this so steep to give us an angle 90, the slope will be undefined. So we have this negative slope. We took the slope or the negative value, came to the position and stretched also to cover the time. So the negative slope of the velocity time graph means negative acceleration, while the positive slope will give you the positive acceleration. And this also points to the fact that acceleration is constant. So it means that this motion is having a steady change in acceleration, which we can call the constant acceleration. Okay. This is clear, so we don't have to, even in our checking, understanding of class exercise, we didn't have to emphasize this because we did a lot of emphasis on this in the last class, okay? The only difference is the change in the axis value. Otherwise, it follows the same pattern. Okay. So move to a constant acceleration. We already have an idea of how a constant acceleration will be represented in a graph. A steep slope. Now, when we say constant acceleration, what exactly do we mean? We're referring to that acceleration that is steady. Okay, it does not change and the velocity is changing in a steady manner. So the acceleration has a constant value. If we look at this graph, it's a typical graph representing a constant acceleration. We see the dotted positions there. They have equal spacing, which is implying a steady acceleration. Okay, so if we take the slope of this velocity time graph, it will give us acceleration. So we try to put a value to this slope. 27, change in y-axis over change in s-axis, give us the slope of 18 meters per second squared. Okay. So this is a typical example of a steady or constant acceleration graph representation. Now, let's look at these two graphs, the figure A and B, which is the acceleration and velocity time graph for motion with constant acceleration. Now, if you have a graph that looks like this, or a graph of constant acceleration, in the velocity time graph representation, it will point this way. Or when you have it in the acceleration time graph representation, it's going to point the same way we just converted this, took the slope, came to the position, and stretch it to the time range, okay? So, but this B part will take us to the next discourse, okay? Which is establishing equation for the position, velocity, and relationship between both in a constant acceleration moving state, okay? So we'll have this as the graph of velocity time graph. Remember in our last class, we discussed a second way to find your displacement or to find the velocity from a time position time graph. So if we go by that method, we'll be able to get from this velocity time graph the displacement. Okay. So if we go by the method of the second option we discussed in our last class, which is taking the area under the graph. So we have this marked out area as represented in the shaded part of this graph. So if we want to take the area under this graph to mean the displacement for this graph, we have two shapes, a rectangle, which is represented with the Vx initial, and then the triangle represented with this AS change in time. Okay, so to get this, if we're able to get this equation, we'll be able to establish the three basic equations that can express perfectly the time constant acceleration. All right. So from this particular diagram here, this figure B is where we got these three equations, this, and this. And how did we do that? We recall that the equation for acceleration is the change in velocity over change in time. So acceleration AS is equal to change in velocity over change in time, which can be expanded to mean final minus initial. And we can also expand this to mean final minus initial as well. Okay, so we collapse by writing it as change or delta Vx. All right, so if we have this expression expanded this way, what we did was to make the final velocity the subject of formula here. So we'll have something like this, cross multiplied. The straight line expression gave us V final minus V initial equal to acceleration times change in time. Okay, so if you move this and it crosses the sign of equality, it becomes positive to give you V final minus V initial plus the product of acceleration and time. This particular equation is what we call the velocity equation for an object with constant acceleration. Okay, so when we're given any question and we're able to establish that the pictorial representation of that question gives us something like, or something we can term an object moving with a constant acceleration, we can employ this equation to look for either the initial value of or any of the parameters seen in this equation. Okay, so the second one, which is the position equation for an object with constant acceleration, we used the second method for deriving position from velocity time graph to get this. Okay, so from the shaded portion above in that figure, we see that we have the rectangle and the triangle. So the area under the graph will give us the sum of both shapes. So the area of a rectangle is, we already know, is half base times height. Then for triangle is half base times height, and for rectangle is length times breadth. Okay, so this times this, and half base times height. Half this times this, and this times this give us that. Okay, so the product of this gave us the rectangle, and then half base times height for the triangle part. So taking the sum of these two equations, we'll have the final position to be final position equal to initial plus the product of velocity and time plus half base times height. Okay, so we just use the parameters here, substitute into the mathematical equation that we know to give us this. And this equation is what we call the position equation for an object with constant acceleration. Okay, so the last expression of that, because we have three basic important equations when treating constant acceleration or handling problems with acceleration. And these are the three equations that are represented in this slide. Okay, so we'll have the relationship between these two, that is relating the velocity and the displacement for constant acceleration motion. And how did we achieve this? We took this equation, made change in time the subject of formula, then substitute into this to get this one. And I'll encourage that we'll practice this substitution because it could be one of the things to practice in class. And then I don't want to call it quiz or test. It depends. It can come in any form, but just practice this. We have about 4 steps that are hidden here. Taking the velocity equation, make time the subject of formula, substitute into the position equation to actually get the relationship between the velocity and displacement for constant acceleration motion. So that's how we got this expression here. Okay. Are we good? Do we have any questions so far? Should we proceed? I want to hear response.
Sure.
Okay, thank you. All right, so let's take one example. Okay, so we'll have this example. As you drive in your car at 15 meters per second, just a bit under 35 miles per hour, okay? You see a child's ball into the street. You see a child's ball roll into the street ahead of you. You know, your instinct to tell you to stop because the next will be the boy, okay? When you're driving, they make the statement a lot. If you see the child's ball, watch out because the next is the boy. So you hit your brake and stop as quickly as you can. In this case, you came to a rest at 1.5 seconds. How far does your car travel as you brake to a stop? Okay, this question is not like the first one that had implied values. This one is just straightforward. It's asking you time. You know, it's about distance. How far? What did you cover in this time and with this speed? Okay. So how did we answer this question? First, we pictured the motion of your car using the velocity graph or velocity vector representation. Okay. So we engaged motion diagram, used our understanding of vector representation to get the velocity graph of the car. Then from the velocity graph of the car, we are able to deduce the direction of the acceleration. So that brings things into perspective for us. Okay. So you're coming at a speed, you know, the longer the arrow, the bigger, or yeah, the bigger the magnitude, which is the speed. Magnitude is the speed is the magnitude of velocity. Okay. So if speed is the magnitude of velocity, we are able to tell the magnitude of acceleration, which is the rate of change of speed, that is in velocity, okay, from the definition, because some of our practice questions use the word magnitude of acceleration. It's nothing strange, but it does not directly mean velocity is the magnitude of acceleration, no, okay? So we see the length decreasing till you got to a stop. We just assume that you're moving to the right, okay? Whatever direction you move now, the acceleration arrow will move in the opposite way because the acceleration is actually decreasing, okay? So you are slowing down, the acceleration vector points in the opposite direction. You remember when we analyzed the first 2 slides, when you're speeding up and when you're slowing down, how to identify the direction of acceleration. So we see the acceleration pointing to the left. That automatically tells us something. When acceleration points to the left, what is the sign? Good. Okay, so we picture this, then we make a graph. We have the parameters given to us, 15. So we know that the car is already at 15 meters per second. it slopes down to a stop at 1.5 seconds. So we have been able to picture the diagram, put values to it, then we can now go to the mathematics of the question, okay? So using the basic formula, acceleration equal to change in velocity with time, we expand this, the change in velocity, final velocity, you came to a stop, so you were not moving at all, which is 0 meters per second. Then the initial, which is from the point you started braking, it's minus 15 meters per second. You know, the minus sign is just telling you you're coming to a stop, okay? But the magnitude of the value is 15, which is the speed, 15 meters per second. So we did that and we reached the final solution for your acceleration or the acceleration of the person driving that car to be 10 meters per acceleration per second squared. Okay, so this information will help us in getting what exactly the question required of us, which is how far, that is the distance. So we took the position equation for object with constant acceleration, this same equation here. Oh, this equation, sorry. So we substitute our values into the equation, which is a final distance. So the final distance, what we did was to move this to this side to give us the change in x, which is what we are looking for. How far, the distance that was covered, which will give us like the final to the initial to final for that range of motion, okay? So we'll have this equation modified to this just to give us the change in x. This one is just change or delta x. So our v is known, 15, time 1.5 plus half acceleration is known and the time is known. And we got 11 meters. So the distance covered for that experience is 11 meters. So we see how we're able to use the information we have about the position time graph, velocity time graph, stemming from equation of acceleration to solve simple life problem and put a figure to the whole experience. So we can say that this person is moving at so speed, has this acceleration and covered this distance. Is that not interesting? This is what makes physics interesting, putting figures to life scenarios, okay? So let's just quickly discuss how we can easily picture the best way to solve problems when it comes to this kind of motion in dimensional problems. That's motion in 1 dimension, 2 dimension, and all etc. Okay. So we followed simple or basic things that we already know. The first thing we did was to identify the important element of that problem. Okay. From the statement given to us, we collected the information and what we need to solve the problem. Because you cannot just jump into solving that problem given the parameters you have. Okay, you analyzed, collected the important information, put what you have into perspective, that is making pictorial representation, putting numbers to it, then you spend most of the time on the steps, because once you get the steps right, then you are good to go. So how did we do this preparation? What did we do first? We drew a picture of what was described. That is, we modeled the problem. We model the problem to identify the important elements in that problem. The important elements of the given problem gave us the additional information that we need to get the solution to what we want. So we collected the necessary information, that is, put the values. Then we made the required conversion, which are the things we do preliminary to the calculation by, okay, I need A and I can get it from B. B was given to me. So I'll find a formula that can actually give me B from A. Okay, so we did the preamble calculation by looking for the acceleration first. We also did it in the first example we saw by calculating or converting the units to the units that we can work with. That is, we converted the mile per hour to meters per second, which is the unit we can work with. Okay, so after getting or collecting all your important information from the question, we move to using the mathematics to get our answer. Okay, so we have equations that already tells us, okay, when this happens like this is what you do to get your answer. So we applied those equations given to get our final answer. Once you have your final answer, then you can look at the answer. Does this answer make sense? Is it realistic? If you have a question and then the answer gives something like a bicycle velocity, final velocity is 100 miles per hour. This is unrealistic. Can you ride 100 miles per hour on a bicycle? Unless the person is a cartoon character that can just move. All right. So those are the kind of analysis we do when we solve physics problems. So you can actually see the section on page 54 of the test. That is the approach 2.1 section. Okay, it's a summary of what you have in these two slides of strategy to solving problems. Okay, so we're going to use the next 10 minutes to check or look at simple quiz or questions about what you have learned today. All right. So I expect response verbally or in chat on this, okay? Before we go, does anyone have any comment or question? Okay, I take the silence to be no. All right, so this 4-motion diagram that we have, we're going to rank this motion diagram by the magnitude of acceleration, ranking them from A to D. Okay, so how do we do this? We said, remember I used the word magnitude of acceleration. And I was explaining that earlier by saying the magnitude of acceleration is actually the rate of change of velocity, which is actually the rate of change of speed. Okay. Okay, we'll talk about that. Somebody's asking, does anyone know where to meet for lab today? Please, can somebody answer verbally? Where are we meeting for lab today?
In the Brody building at 232, like room 232?
Yes, room 2-32, okay? So, how do we pronounce this name? Kathleen, are you there?
Yes.
How do you pronounce your name, please?
Caitlin.
Caitlin, did you get the answer? Do you know where we're meeting now?
I'm still thinking about it.
You have to think the building You know the building, then the room on the physics floor, which
Oh,
is
yeah,
the.
yeah. I got that.
Mhm.
Yeah.
Okay,
Thank you.
you're welcome. So we have C, C, C as the answer. Fine. Look at the answer C and picture this. A is equal to B. Remember what we're looking at is what? The magnitude of acceleration. We're not talking about the direction now. We're not talking about the signs. Look at the A. Okay, to do it in the crude way, if you count these arrows, they are the same number. If you rearrange, they all have the same shape or magnitude. So this one is the acceleration is moving this way. Okay, acceleration is this way. It's moving. This one, acceleration is moving this way. So A is equal to B, but the only thing is the direction, right? This way, this way. C is equal to D, A equal to B equal to C equal to, so we took the same arrows and rearrange. This is a start, this is a start for this. The first motion, is it speeding up or coming to a stop? The A. If you look at this arrow diagram, is it speeding up or coming to a stop?
Speeding up.
Good. So the B is coming to a stop, right? So you remember how we said that to recognize the speeding up and the one that is coming to a stop, the vector, a velocity vector arrow, and the sign for acceleration will do what? We point in what direction? The same or opposite? Before we said this is speeding up, in terms of acceleration, when an object is speeding up, is the direction the same or in opposite with acceleration?
It would be the same direction.
Good. Okay, some people responded, same, yeah. So we see how A became equal to B and equal to C and D. So that is how we got the answer to be C. So you try different, just flip the textbook, you see several vector diagram representation like this. Ask yourself, what is the direction of acceleration here? Is it positive? Is it negative? Is it speeding up? Is it slowing down? That's one way to remember everything we've discussed today. Okay, so we'll have another one. We'll have the 4 diagram for motion. The question is, which motion diagram corresponds to a positive acceleration and the motion diagram corresponding to a negative acceleration, using the idea of speeding up, slowing down, direction left and right. When acceleration points to the left, what will be the sign? When acceleration points to the right, what will be the sign?
Positive.
Yeah,
Positive.
positive. When it's going to the left, negative. Okay. So we look at A. Which way is acceleration pointing to?
To the right.
Positive.
So the first question says which one corresponds to the positive acceleration. That means we are looking for acceleration that is pointing to the right. Okay. So this one, the acceleration is pointing to the left. You see, it's going from short to length, longer length. So it's going this way. It's going this way. So we're able to draw in the first case that A, short to length, C, right? Then we'll have our answer. Okay. So we'll have several practice. This look like the same practice of the direction of acceleration. Just picture, look at this question. How does it make sense? How did the answer correspond to the statement and what we discussed in class today? Okay. So we'll have some examples of problem you can try your hands on.
I have a
And
question.
Mhm.
If we go back up to the ones with the lines and the arrows, I just wanted to clarify something just because I'm a little confused just in my head, but
Here, this
yeah,
one.
yeah, like one of those ones, yeah.
Okay.
I just wanted to clarify that, like, say, like with C, because it's going from the longer arrows to the smaller ones, it's like slowing down, right?
This one, the C.
Yeah,
Okay.
because if it starts on this side and then it's like longer at the beginning and then it goes smaller, it's like slowing down.
It's slowing down.
So like
For
B and C would be slowing down, whereas A and D would be speeding up because it's wherever the start is. Like, because on A and D the start is like it's smaller and then it gets longer and longer, whereas with B and C it's the start is longer and then it gets shorter.
Okay, so the description you just gave is in terms of the velocity vector. Okay.
Okay.
When you just look at the start and the length of the arrow, you are looking at it in terms of the velocity vector.
Oh, okay.
But when it comes to acceleration, remember in our first this slide, we made a statement here. Okay, we said something about the sign. It's not just based on the direction of acceleration vector point or the object, okay? We said the sign A, the sign for A. So how we define the direction for A, which is the sign? It's not about the speeding up or slowing down.
Okay.
Okay, so let me just use this statement, but not a scientific way to say it. For acceleration, it's going to go from the short to the big arrow. So you are increasing from short to big. So we look at this. This is the start, right? It's speeding up like we described for the example on a moving car that sees the ball, then comes to a stop, all right? But the acceleration here is in this direction. Can you see? Short arrow, longer, longer, longer to longest. Okay, so this arrow for acceleration is in opposite direction to the velocity vector. When they are in opposite direction, it means what? The object is slowing down, coming to a stop.
Okay.
And when it's coming to a stop, the acceleration is pointing positive, okay? Because it's pointing to the right. That is the sign. It's going to the right. The acceleration here is positive.
So
But
A would be acceleration is positive as well, but it's speeding up.
yes.
Whereas
Yes.
C, the acceleration is positive, but
Still
it's
slowing down. Exactly. You got it now.
Okay. Thanks.
Okay. You're welcome. All right. Okay, so we have the section for personal practice. When you go to the chapter 2, I didn't put the pages here, but you're able to trace the synthesis 2.1. Then you study these examples, okay? Then you can try to practice this problem 25. All right. So we'll see in class. Does anyone have question about the lab? Okay, Micha, you can go. Does anyone have question about the lab class today? Was the information provided able to answer all our questions?
I tried to watch the video you uploaded for random errors, but it didn't play, and I'm not sure why.
Okay. Is this unique to her or we all experience this? Is anyone in class able to watch the same video?
Yeah, I watched them this morning.
Okay. So I'll say it's something about your system player or something on your system that could not play the video, not the video link, because it's playing on my system and it played on several systems I tried it on. Okay. But don't worry so much about that. All right. It's just to give you an idea. We will not always have to upload videos because this is the first lab. We just want you to feel relaxed, nothing to be anxious about. Okay. All right. Okay, so we'll see in lab today for those of us that registered for the Wednesday lab. We'll have some of us that registered for the Thursday lab, which was moved to Friday. If you have any challenge with the Friday lab, quickly speak up so that we can find a way to reschedule you, okay? And it has to be a genuine enough reason to reschedule you. All right. Thank you so much. Have a great day.
All right, thank you. See you later, I guess.
See you later. Bye-bye.
Just a quick question.
Okay.
Will we get like a data sheet for the lab today in the lab?
No, you won't be given any of such. You're expected to, you're not turning in the report immediately.
Okay,
In the lab, I'll tell you the day I'll expect you to turn in the report.
okay,
Whether you'll be doing that online or in person, it's going to be up to you. That is, if you're going to have a printout for me but we'll have sample of what we expect you to report. I gave you one sample of the report.
yeah, I saw that one.
So,
I was just wondering if we just write that on like loose leaf
yeah.
all over
So,
like everything?
yes, your result can be on a sheet of paper that you work with. And sometimes you'll be working with laptop. Sometimes you'll be working on a sheet of paper. If you have to take readings on the laptop, you can screenshot and email to yourself because it will be connected to the internet. And when it's not, you just snap with your device
Okay,
or write down something.
okay, and
Okay.
we'll talk about that more in the lab.
All right.
Okay, sounds good. Thank
Okay.
you.
Yeah. Bye-bye.
Bye-bye.